Graphing sine and cosine functions. So now that we know about C and D, we need to adjust our graphing procedures a little bit. Let's take a look at some examples. Our first example, the function y equals negative sine of 4x plus 2. Let's fill in some of our features. The basic starting shape. I see that negative in front of the sine, so that tells me I have a reflected sine graph. That's the picture I'm about to draw. The valley and the hill. Remember, it goes middle, low, middle, high, middle. Very important. The amplitude, well, the A value is clearly -1. The negative tells me the reflection. We took care of that already. The amplitude would be the 1. Period, that comes from the b number, the number multiplying the x. We have a little formula for period. It's 2 pi divided by the b, and I can see that that reduces to pi over 2. The midline, well, the midline is the d number, the number that's being added or subtracted at the end. That's clearly 2. The midline would be the horizontal line y equals 2. You see I didn't write phase shift here. That's because I don't have a number being added or subtracted to the x. So I don't have a phase shift in this problem. How about the x coordinates of the 5 key points? Well, that's the same as always. We start at 0. We end at the period. We can cut the period in half to find the middle number. Half of pi over 2 would be pi over 4. We can cut that in half to find the next number. Half of pi over 4 would be pi over 8. Now I know I'm counting by pi over 8s. So 0, pi over 8, 2 pi over 8, and 3 pi over 8 for that missing spot. The next one would be 4 pi over 8, which reduces to pi over 2. So we've got all those filled in. We have all the information we need now to graph one complete period. We are being asked to show our scale carefully. We want to show the midline. We'll do that using a dashed line, and we want to mark dots at the 5 key points. Well, the x scale is straightforward. We've already written down the values that we need. On the y-axis, it's very important that you mark the midline location, and then you have to use the amplitude to think about how much higher and lower you're going to have to go. The amplitude is 1, so I know I'm going to have to go 1 higher and 1 lower. Let me add in a dashed line for the midline. And then here's where the basic shape is so helpful. We know that reflected sine starts at the middle. The middle is the midline, so it's going to start right here. Then it goes to the low. The low point at the next x value is 1. Because the amplitude is 1. It only goes 1 below the midline. Then we're back to the middle. Then we're up at the high, which is 3, 1 above the midline. And then we're back to the middle. Well, connect the dots and you've got your graph. Lastly, we're asked for the range of the function. Let's just use interval notation. I think I can tell pretty easily that the smallest y value is 1. And the biggest y value is 3, and so my range would be all numbers between 1 and 3. Okay, let's try another one. This time we have y equals -4 cosine of pi parentheses x plus 1/4. Looks like this time we're going to have to deal with a phase shift. Let's write down our information. We've clearly got a reflected cosine, so that would be this shape, which we like to call the ghost. The amplitude, I can see the A is -4. The negative was for the reflection, so the amplitude is the 4. Period, let's see, here's the B right here. B is the number multiplying by the x. It is multiplying the x just on the outside of the parentheses. So my period would be 2 pi divided by that B number, and that's going to simplify to be just 2. So my period is 2. The midline, I don't have a plus d sitting here at the end. That just means there is no vertical shift, so the midline is where we always expect it to be, right along the x-axis, right at y equals 0. There is a phase shift this time. The phase shift is the C, but remember, C is the opposite of what you see. The equation says 1/4, but I know the phase shift is -1/4 because of that built-in minus sign. Our strategy with the phase shift is basically to ignore it until the very end. And let me show you how that works. My next job, I want to write down the 5 key points, the x coordinates. not with the phase shift. I'm going to write down what they would have been without the phase shift. In other words, I'm doing the same thing I always do. I'm starting at 0, I'm ending at the period. Obviously, if the period is 2, this would be 1. Half of that would be 1/2. I'm counting by halves. So 0, 1/2, 1, 1 1/2, which would be 3 halves, and then 2. Now look what it says down here in the graphing part. It says first show a dashed graph without the phase shift. I'm going to pretend there's no phase shift. I'm going to draw a picture of what this thing would look like, and then at the very end I will use the phase shift to create the final graph. Okay, let's mark down our scaling. Let's see, on the y-axis the midline is 0, that's convenient, and then the amplitude is 4, so I at least need to show that, and then down to -4. Okay, let's mark our 5 key points. The reflected cosine function starts at the low, then goes up to the middle, then the high, the middle, and the low. I've drawn it in dashed because this is not the final answer. This is what the graph would have looked like if there hadn't been a phase shift. Now we will adjust it for the phase shift, and all I have to do, the phase shift is -1/4. That means shift this graph 1/4 to the left. I essentially need to pick up every one of these x coordinates that I had and shift it over to the left 1/4. In other words, subtract 1/4 from each of these values. Let's see, my current tick marks go by 1/2. I know that 1/4 is just half of a half. So let's mark down the points we're talking about. My first x value used to be at 0. Now it's going to be here at -1/4. My 1/2, if I subtract a fourth from that, I'm going to be at +1/4. If I subtract a quarter from 1, I'll be at 3/4. Here I would be at 1 1/4 or 5/4. And here I would be at 7/4. My new tick marks essentially count by 1/4. 1/4, 2/4, which is 1/2, 3/4, 4/4, which is 1, 5/4, 6/4, 7/4, 8/4, which reduces to 2. So I've had to mark on. I do want to have the scaling shown clearly. I should be able to tell where the 5 key points are. So I've got those marked on. Now I can move those previous points to the right spot. Just move each one to the left by 1/4. So this dot would move here. The second dot is on the midline. It'll be here. The third dot will be at 3/4, 4. The fourth dot here at 5/4. The last dot here at 7/4. And now I'll connect this with a solid graph. This is my final graph. I think the only thing missing is the midline, which I will also draw in dashed. And I've got my final picture. This is the approach you should use. Draw the graph first without thinking about the phase shift. You'll show me that as a dashed graph, and then apply the phase shift to obtain your final graph. Let's look at one last example. We've got y equals 2 sine of 3x minus pi over 2, and then -2. Now, if you look at this carefully, you'll notice something is wrong in this part here. Where's that other set of parentheses? The pi over 2 isn't supposed to be subtracted from the 3x. They're supposed to be something just subtracted from the x. Well, I have a preliminary step I'm going to have to take here. I'm going to have to fix that. I'm going to have to rewrite the equation in that factored form. All of our results are only true in that factored format. So here's what it'll look like. I have y equals, most of it's the same, 2 sine. And then essentially what I need to do is I need to factor that 3 out of those two terms inside the existing parentheses. I need to factor it out so that it will look like the right format. Well, factoring is really just dividing. 3x divided by 3 is just x. Notice that if I were to remultiply 3 times x, I would get back to 3x. How do I figure out what goes in this spot? I just need to take pi over 2 and divide it by 3. Well, that's the same as multiplying it by 1/3, 1 over 3, which of course is pi over 6. The number in the parentheses now is pi over 6. To check yourself, what you would have to do is distribute that 3 back. 3 times x, 3x. 3 times pi over 6 would be 3 pi over 6, which reduces to pi over 2. So we did it correctly. You've got to put the equation in factored form first. Now we can follow our usual steps. We've got the regular sine function here, so that's the hill in the valley. I can see that the amplitude is 2, that 2 in the front. The period, let's see, it's 2 pi divided by the b. The b is 3. It doesn't reduce, so 2 pi over 3. The midline, that's that d number at the end. I can see that that's a -2, so y equals -2. And the phase shift, let's see, it says x minus pi over 6, but I know the c is the opposite of what I see, so the phase shift must be positive pi over 6. I will ignore the phase shift until the very end. The 5 key points before the phase shift start at 0, end at the period. Let's see, half of 2 pi over 3 would be 1 pi over 3. And half of pi over 3 is pi over 6. I'm counting by pi over 6's. So pi over 6, 2 pi over 6, and then 3 pi over 6, which reduces to pi over 2. The last one is 4 pi over 6, which reduces to 2 pi over 3. That's all the information I need. Let's mark down our scaling. Let's see, on the y-axis, the midline's at -2. The amplitude is 2, so I know it's going to go up 2, and it's also going to go down 2, so that would be down here to -4. So I think that's plenty of scaling there. Let's draw on the midline, that's dashed. And then the regular sine shape starts at the midline. Then it goes to the high, back to the middle, to the low, and back to the middle. And then I'll connect my dots with a dashed graph, since this is not my final answer. Okay, this is what the graph would have looked like if there was no phase shift. All I have to do to get my final answer is deal with the phase shift. The phase shift is positive pi over 6, which means take that dashed graph and shift it to the right by pi over 6. Now, pi over 6 is a wonderful phase shift to have because I'm already counting by pi over 6's. I just need to move every dot 1 tick mark over to the right. I'm going to need one last one here. Let's see, I was counting by 1 pi over 6, so 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. The last one would be 5 pi over 6, and then shift over each dot. So this dot goes here, this dot goes here, and so on. Every dot is moving 1 tick mark to the right. Connect the dots, and that solid graph is the graph of the function for one period. We have all the 5 key points marked. We have all the scaling we need to tell the coordinates of every single key point. That's the standard, and so we're done. Now, you need to learn how to do this by hand, as I've demonstrated. But remember, the calculator is still a great tool for checking. Let's take a look. So I've typed the equation into the y1 line. Notice that I just used the original one. I didn't use the factored form. The calculator certainly doesn't care, and it seemed to me easier to just type it in that way. I will have to think about the window. I'll just try to replicate what we had on the paper. I think our x values went from about negative pi over 6 up to positive 5 pi over 6. So negative pi over 6 there, positive 5 pi over 6. We were counting by pi over 6's. And then on the y, negative 4 to 4 looks about right, and counting by 2's I think we did. And I'll hit graph, and I should be seeing basically what we saw on the paper. If you're still not convinced, you could use the trace feature to find specific points. For example, on our graph we have the point 2 pi over 3 comma negative 4. Well, what I can do is hit trace, type in 2 pi over 3, and then hit enter, and sure enough, it takes me to negative 4. And so that convinces me that yes, we've drawn the right picture. Thanks for watching.